Okay, I think we can get started. Hello, everyone, and welcome to the civil seminar. Uh, Today, we are very pleased to have Dr. Farshid Vahedifard with us. Dr. Vahedifard is the CEE Advisory Board endowed professor and an associate professor in the Richard Wallace School of Civil and Environmental Engineering at Mississippi State University. He has over 18 years of experience working in the area, both in academic and in industry of geotechnical engineering, and he's tackling problems associated with climate change, resilient infrastructure, and energy. He has been quite successful in receiving projects and funding over $5 million from 2012 from different funding sources. And he has advised over 40 master's and PhD students with 150 refereed articles. Dr. Vahedifard has received several awards. He's a fellow of the ASCE, and some of the awards included 2021 MSU Annual Research Award and several others. So his research is mostly in the area of the resilience of infrastructure and communities to extreme events under the climate change, the multi-physics processes in variably saturated soils, and energy geomechanics. So today he's going to give a presentation related to a multi-institutional NSF supported project that he has led called the Resilience of Geotechnical Infrastructure under a Changing Climate, Quantitative Assessment for Extreme Events. And the title of the talk is Adaptive and Resilient Infrastructure in the Face of Climate Change. So that will be quite fascinating to hear. With that said, the floor is yours, Dr. Farshid.
Thanks a lot, Reza, for the very kind introduction. Good afternoon, everyone. It's great to be here, and I'm very happy to be here and share some of our results from our recent study on this topic. And let me start sharing my screen. Do you see the cover page, Reza?
Yes.
Okay, let's start. Today I'll be talking about adaptive and resilient infrastructure in the face of climate change. To start with, let's first look at some of the recent events and some of the statistics. And the main question that I would like to pose that all these extreme events, disasters that we hear almost every day in the news, are they rare events or a picture of the new normal that we have to adjust with? Just in the United States, 2020 was the sixth back-to-back year that we had 10 or more billion-dollar natural disasters and extreme events. Over the last 41 years, as you can see on the screen, years with 10 or more billion-dollar disasters are 1998, 2008, 2011 to 2012, and 2015 to 2020. So as you can see, we see an increasing trend in terms of the number of billion-dollar disasters. Just in 2020, we had a new record in the history with basically a new record in terms of the number of billion-dollar disasters. In the first 9 months, we had 16 events. By the end of 2020, NOAA just published the new data, and we had 22 separate billion-dollar disasters, which is a new record in the history of the United States in terms of billion-dollar disasters. Recent studies show that we are short in terms of funding for improving our infrastructure, and the amount that they're suggested is over $27 trillion. that we need to spend over 10 years to bring our critical infrastructure to in a good condition. Overall, in the United States, just based on a recent report by ASTE, the overall grade of our infrastructure system is D. Of course, that's not the grade that you would like to get, but that's what we are. That's where we are, and we need to invest more. Now, what I want to do, and here is a map of different type of billion-dollar disasters that we had in 2020. As you can see, we had all kind of different issues related to uh, uh, in 2020, they ran out of names for hurricanes. Actually, they started, they named hurricanes, but then they ran out of names. So they started just naming them with like alphabet letters, A, B, C. We had wildfires. 2020 was the most active wildfire year in the West Coast, in the history of the West Coast. Hurricanes, tornadoes, and all kind of different weather and climate disasters. So as we can see, we see a very obvious trend, increasing trend in terms of billion-dollar disasters. This is in part related to anthropogenic climate change, and it has to be also more exposure due to population, due to urbanization in several areas, the combination of climate change and the more exposure of communities. Those all together have caused more increasing trend in billion-dollar disasters. One thing that we need to understand is we can definitely see an impact of human activities on many aspects of climate change. The figure on the bottom right shows temperature trend versus time for three different cases. The black line shows observation, the blue band shows models using only natural forces, and the pink band shows both natural and human forces. And as you can see, the observation is pretty good match with the model using both natural and human forces. What does it mean? It means that there is this clear anthropogenic climate change that we need to consider and take it into consideration. Let's look at some recorded data. This is a map published in 2010 and 2009 in terms of increases in the amount of very heavy precipitation in the United States. On average, over the past 50 years, the United States has experienced an increase of 20% in the amount of very heavy precipitation throughout the country. This can be as much as 67% in the Northeast, and the lowest is 9% in the Southwest. But overall, the nation has had 20% increase in the amount of very heavy precipitation. Those are recorded data. And let's look at some projections. Here is a study that we published in 2018. We looked at the intensity and frequency of extreme events projected using projected models. And we wanted to see how those intensity will change for several major urban areas throughout the country here in the United States. And you see on the bottom right, the map of the area that we looked at, the cities that we looked at. And for each city, you see basically the current IDF based on historical data and projected results using two different RCPs, basically, and with the confidence interval. Overall, what we saw was over the next 50 years, we should expect an average about 20% increase in the intensity of extreme precipitation. So that's one thing that we need to consider. In this study, one thing that the notion that we adopted was the notion of non-stationary. And it means that this is not, of course, my area. I'm not a hydrologist. So what it means that the notion of non-stationary means that we consider changes in the statistics of extreme event induced by climate change. So that's unlike most of design guidelines and codes that we currently use, which use the notion of stationary which means that there is no change in the statistics of extreme event. Not only on the intensity of rainfall, we also looked at the frequency of rainfall, extreme precipitation in the future. Here in this figure, you see the changes in return period, the frequency of like 50-year event and uh, um, uh, for different locations. The way that you can look at this, and also we have 100-year data on this figure, the way to look at this figure is what we call 50-year event today, what's the frequency of that event in the future? For example, I'm on the top left figure, if you see, for example, for Salt Lake City, what we call a 50-year extreme rainfall now, it will become more frequent and it will happen every about 40 years in the future. So you see that not only the intensity of extreme event is increasing, is worsening, it's also the frequency of extreme event is changing. And you see the results for different cities. Well, it can be uh, pretty bad in some locations, like Salt Lake City. As you can see, a 50-year event will become like 20-year. It means that we will deal with more frequent, event. And I'm sure you have heard in the news as well for like flooding. You hear all the times that was a 1,000-year flood, but then you hear again 1,000-year flood again. So those 1,000-year floods are not supposed to happen every year. But there is a clear indication that we see an increase in frequency of also extreme events. So what does it mean? Those are great data. Those are great findings in terms of changes in the statistics of extreme events, extreme precipitations, or flooding. But by training, I'm a geotechnical engineer. I'm more interested in design. I'm more interested in analysis. What does it mean for me? And that's something that I've been always interested to explore. I always attend those presentations, AGUs. I'm always fascinated, excited about seeing all those advances in, climate modeling. But I always ask myself, what does it mean for us in civil engineering in terms of the structures, in terms of geotechnical engineering? How can we bridge this climate science, hydrology, hydroclimatology to our daily practice in structural engineering or daily practice in geotechnical engineering? And that has been the area that I've been trying to work over the past several years. First, we have to understand the interaction between those climatic drivers with our infrastructure, in particular, in this case, for like an earthen structure or slope. Here in this cartoon, you see some of the interactions that you would expect and you would see between like an earthen structure or slope and climate. You can see all different type of interactions. It can be the impact of those climatic events on soil surface, impact on desiccation cracking, in terms of the impact on hydraulic loading applied to the structures, in terms of initiating, cracks. Those are some of the climatic interactions that you can expect, and we see that almost in like a daily practice. Now, what does it mean when we have more extreme precipitation? What does it mean when we have more frequent flood? For us, for geotechnical engineering practice or structural engineering practice, it means that the structure will be imposed to more frequent or more extreme loading conditions. So for us, we need to be better prepared for a new pattern of loading conditions. At the same time, they can also impact the supply that we have. What is the supply? The supply is, for example, in this case, it's shear strength of soil. And that's what I did. And I tried to basically look at the impact of those climatic change feature on geotechnical properties. I'm not going to get into details of what we have here in this table, but what we did, this is the paper that we published in 2018. We looked at each climate change feature, and we wanted to see what's the fundamental impact on soil properties and what's the practical impact. For example, we know that we have increased, more intense precipitation. What's the fundamental impact? We will have more rapid soil wetting and we can have overland flow. What's the practical impact in terms of geotechnical application? we will have rapid changes in soil suction, uh, uh, which can lead to higher risk of failure. We can have more uh, risk of erosion and mass wasting. Those are other issues. And the same thing for other climatic trends. We looked at sea level rise, and flooding, for example, higher sea level means that you're applying higher hydraulic loading to the structure, and it will increase pore water pressure that you have, and it can also increase hydraulic gradient that will be applied to the structure, to the earthen structure, which can increase the probability of piping or soil erosion or overtop. So we did the same thing for all other, climate change features. And what we did, what we learned was there is a great um, class of problem here. In all these cases, we are dealing with coupled processes in variably saturated soils and in the rocks. So, increased temperature impose more heat to soil. And we are talking about more intense precipitation. We are talking about more intense hydraulic loading. The same for flooding. So we are dealing with coupled processes in soils. Now, how do we tackle that? How do we um, understand the impact, quantify the impact, and adopt and prepare for that? It's great, but this is not a classic geotech area. And that's where we need to go beyond our comfort zone and start talking to other people. And for that reason, the key to address climate resilient infrastructure is collaboration. There are different areas that we need to work with. We need to learn from and try to share information and adopt knowledge and then adopt the data. I listed some of them, but doesn't mean that those are the only areas that we need to work. But the areas that I listed are literally the areas that I've been working with them over the past few years. As a part of this study, basically, well, we recently had a project supported by National Science Foundation. In that project, we wanted to answer three mm, main questions. Basically, in short, we wanted to see the impact of the, the new patterns of extreme events on both supply and demand. What is the supply? The supply is shear strength of soil, compressibility of the soil. What is the demand? The load that we are applying. So in the first step, we wanted to see the impact of climate change on the rate and variability of climatic extremes. And then we wanted to understand the soil behavior under thermohydromechanical processes imposed by climate adjusted extremes. And then in the last step, we wanted to take it to the next level, to the structural level. And we wanted to understand short-term and long-term behavior of geotechnical structure or structure under the new patterns of extreme events. In this presentation, I will present two examples or two case studies. One example deals with analysis to quantify the impact on existing infrastructure. That's one aspect. But remember, in our daily practice, analysis is one part of what we are doing. Another critical component is design for future infrastructure. So the second part of my presentation is how we can deal with new patterns of extreme events and how can we incorporate them in our design practice. There is one big challenge over there, and that's the uncertainty with climate projections. We know that there's a huge variability among different climate models. And what we are trying to do, we are trying to address that uncertainty while avoiding, over investing in design upfront. So those are two examples or case studies that I selected for this presentation. I thought that those will provide a good overview of how we need to deal with uh, new patterns of extreme events under changing climate and make sure our infrastructure is safe, the existing infrastructure is safe, and also our future infrastructure uh, uh, systems are resilient and safe against future extreme events. So with that in mind, uh, I present two examples. Please feel free to ask questions about each. There are several more examples or applications we explored, but for the sake of time, I'll be presenting these two examples as representative of design and analysis. The first example is an analysis example. We wanted to quantify, um, we wanted to quantify impacts. The example that I selected is modeling rainfall trigger landslide in an area near Seattle, Washington. Uh, uh, that northwest area of the United States is quite vulnerable to rainfall trigger landslide. You see all different types of landslide happening over there. It's quite common to see landslides happening during rainy season, and it's a major threat to population and community. In the first part of this study, we wanted to see, okay, for those landslides, what will be the impact of climate change on the landslide risk that they deal with that in that area. So what we did first, what we wanted to do, we wanted to quantify the impact on the main driver. What is the main driver here? The main driver is extreme precipitation. So what we did first, we looked at historical rainfall data in the area. We had historical intensity, duration, frequency curves. We call them baseline or historical IDF curves. At the same time, with my colleagues, my hydroclimatologist colleague, they use their non-stationary framework to develop projected future IDF curves for the same study area. This is based on a framework called NEVA or non-stationary extreme value analysis, which consider the changes in the statistics of extreme event. So we had baseline historical and also projected future extreme precipitation for the area. Those were based on uh, bias corrected downsample precipitation data for the study area that we were selecting. Now, the next step was quantify the impact of those changes in performance of earthen structures. What we did, we selected a pre-vulnerable slope in the area, and we used a set of fully coupled finite element simulations to simulate the slope under an extreme precipitation event for different return periods for different rain duration. You see here, what you see here, it's part of the analysis that my colleagues did to extract, to develop and obtain future non-stationary IDF curves for different locations. On this particular case study, we extracted the data for the Seattle area. Here is basically the model that we created for that landslide. This is a pre-vulnerable area, and we selected this site as a representative of highly prone area to landslide risk. On the top left, you see the finite element model that we created. This is a fully coupled hydromechanical modeling. It means that we are considering the interaction between solid and fluid interaction. We are considering variably saturated soils. In that area, water table is not on the surface. So you have an unsaturated zone, you have saturated zone. And as you can see on this cross section, we consider both zones. And on the right, you see material properties that we use. And then we simulated the slope under infiltration condition. Here are figures showing IDF curves with for the study area for baseline and projected data. For projected data, given the variability between climate models, we consider lower bound, median, and upper bound for different models. And then what we did, we applied that infiltration, we applied that rainfall as infiltration boundary condition to the slope, and we have three stages. First, we created initial condition. We use annual rain to generate initial condition. For the stability of the slopes, initial moisture condition plays a critical load on the performance of the slope after any extreme rainfall. So we ran steady state seepage analysis using annual rain. Basically, we wanted to see before an extreme rain, where do we stand in terms of pore water pressure, initial stability of the slope. And then we applied the extreme precipitation as infiltration boundary condition on the top of the slope in a transient seepage fully coupled hydromechanical modeling. And then we also look at the performance of the slope after the rainfall. After the rainfall stopped, we wanted to see how the performance will evolve. So we looked at the performance of the slope before the rain, during the rain, and after the rain. And at the bottom, you see basically strength reduction factor contours for the slope at different times. In a simple language, strength reduction factor is a measure of the stability of the slope, or in a more common terminology, we use factor of safety. Strength reduction factor is a factor that we get from finite element simulation, and it's kind of equal to what we term as factor of safety. So it shows that how factor of safety or strength reduction factor changes with time in the slope that we have. So we did this with baseline, and we did the same simulation using future data to see the impact and compare them. The main goal is to quantify the impact of climate change. We wanted to see how the factor of safety of the slope will change when we consider the effect of climate change. What's the implication? The implication is we will see if we ignore the effect of climate change, how much we are underestimating or overestimating the performance of the slope. And these are the results were projected. To get a better sense, let's compare them. And in this figure, I like to draw your attention to the second row, the bottom row. You can see strength reduction factor on the first row, but I think the part that is more interesting to look before getting into too much details is relative change in factor of safety or strength reduction factor. We looked at three different sections along the slope, section A, section B, and section C. And what you can see here is at different depths also. We looked at half a meter, 1 meter, and 1.5 meters. Just take a look at relative change in strength reduction factor and relative change relative to the baseline factor. As you can see, strength reduction factor can change anywhere between almost like 0 all the way down to minus 200. What does it mean? It means that using historical data can underestimate the impact of extreme precipitation. It means that future data will lower the factor of safety 2 times more than the existing data. So you can see that basically the effect can be significant, and that's not something that we can ignore or overlook. One critical point that I wanted to emphasize is we are engineers. We are still engineers. The point that we are trying to highlight here is we have to deal with climate change issue as an engineering problem, at least in our profession. I'm not trying to convince people that climate change exists or not. And I'm not trying to push that climate change will change everything tomorrow morning. No, that's not my job. That's not my area of expertise. What we have to do, we have to deal with that as another engineering problem. The impact might be significant in one area for one type of structure, but it may not be as significant in another area. So this is site specific, this is structure dependent, but we can quantify that. What we are trying to say that in this particular problem, we collaborated with climate scientists, we collaborated with hydrologists, and we had geotechnical engineers in the team. So we wanted to present a framework to show how a collaborative framework can work to quantify such impact. Again, like any design, we don't use the same prescription for every single design. We go case by case. The same thing here. We can take a quantitative engineering approach to quantify the impact of climate change in each area, depending on the characteristics of that area. and see if this impact is significant or not. So that was the first example that I wanted to present to show how we can analyze and quantify the impact. The second part that I wanted to discuss and share with you was how we can design future infrastructure. Now we looked at the example when we could analyze the existing infrastructure, but then how can we incorporate these new climatic variables or statistics into design of future infrastructure? We talked about um, climate observations and climate models. We saw that almost all of them suggest increasing patterns in several areas. What does it mean? It means that we need to adopt our communities, we need to adopt our infrastructure to the new patterns of extreme. But what's the challenge? The challenge here is climate science does not provide a solid basis for engineering practices. That's the gap that I noticed over the past few years, and that's the gap that I've been hoping to be able to contribute to that, to filling that gap. There is a gap between climate science and engineering practice. They do work on those large scale models, but we deal with the structural scale side by side applications. And that's the part that we can work on it and we can make a great contribution. The main question is, in our design practice, in our infrastructure design practice, how can we consider changes in extreme event and changing climate while accounting for the variability of climate projections? Again, we discussed that you saw on the IDF curve result that I just showed, you saw a pretty wide band of results. What does it mean? There's a large variability. They keep monitoring, they keep improving their model projections. So what we know today is very different than what we knew like 10 years ago. And climate models are continuously improving to increase their accuracy based on what we learn every day. But then when I design an infrastructure today, I'm designing it for the next 50 years, for the next 100 years. How can I incorporate these new changes in extreme events while considering the variability in climate projection and also avoiding overinvestment? Uh, that's a critical question. For this, to answer this question, what we proposed was we proposed to have a risk-based adaptive design framework. And that's the purpose of this part. And to just show a little bit about the variability that I'm talking about, here you see the temperature, annual temperature, and you see basically the sea level rise. You see different projection scenarios starting from RCP 2.6, more conservative, the most conservative, projection scenarios, emission scenarios, all the way to RCP 8.5, the most extreme, the extremist, basically the extremist emission scenarios. As you can see, there's a large variability. The question is, how can we deal with that large variability? What's the framework that we are proposing? In geotechnical engineering, we are used to deal with uncertainty. You all know that when you're talking about soil, you're talking about underground, subsurface, something that we don't see. Unlike any textbook material like concrete or steel, we have very little knowledge about soil behavior. We know that soil has a huge variability. It's a very heterogeneous material. No matter how many boreholes you have in a site, it can be completely different material, like 100 meter or 200 meter away from the boreholes that you have. So we are used to live with uncertainty in geotechnical engineering. There's Zaghi, which is called basically the father of geotechnical engineering, and his colleague Peck, to address this uncertainty in geotechnical engineering, they proposed a small genius method called the observational method several decades ago. Basically, the observational method was proposed to deal with the uncertainty of settlement in foundations. In foundation design, we design the foundation and we predict the foundation will have certain settlement. And based on that, we design the foundation. But our prediction or assumption may not be necessarily correct. Herzog and Peck, they suggested that, we can have an initial design and then we can keep monitoring the foundation settlement. And based on the observation that we have, we can revisit the design. And if needed, we can make adjustment to the initial design. So this is basically based on observation, monitoring, and adjusting the design, revisiting the design if needed. So we adopted the same concept. We said that, okay, we can deal with the climate variability using the same approach, the observational method approach. So we kind of presented an extension of the observational method, initially proposed by Terzaghi and Peck. Uh, uh, what did we say? We said that for your initial design, select a most probable, but not the most conservative based design to avoid overinvestment. This will address the limitation of some of other alternative design methodology, like robust design methodology. Again, we are not trying to go with the worst case scenario. We are trying to say that for each structure, for each type of infrastructure, based on the importance of the project, based on the risk that we can tolerate for that particular project, select a level of risk that we can tolerate. Based on the selected level of risk, select the most probable level of for initial design. Um, and then keep monitoring the structure. Keep monitoring the structure. At the same time, you are updating your climate variable prediction. So you have climate predictions, updated climate predictions. You have new monitoring data. Keep updating the performance criteria, performance evaluation index. For example, if you are monitoring factor of safety or probability of failure, use the updated monitoring data plus updated projection data and recalculate the performance index, probability of failure, factor of safety, whatever, and then see if you need to make any adjustment in the design. That's the whole process. The process will involve 3 steps or 4 major steps. The first step is initial design, construction, then observation and adaptation. Design phases that we have 3 design phases, if you would. The first step is a risk-based initial design. Then we have design with adaptation capacity and adapted design. We try to show each of them on this flowchart. On the top left, you see basically distribution of an extreme. Any extreme, it can be, I don't know, it can be extreme precipitation based on future projection. So if you look at the curve, we set the historic baseline at basically the median. And there is an upper bound case, which is basically based on the existing climate projections that we have. We don't want to go with upper bound, and we don't want to go with historical baseline. What we are suggesting to go with the point between the two extremes, between the two boundaries. And that point will be selected based on the risk threshold that we can tolerate for that particular area, for that particular infrastructure. If the infrastructure that we are building is a critical infrastructure, which may have significant impact on communities, downstream side or, using that infrastructure, we want to minimize the risk. But if it's not a very critical infrastructure, we can be more flexible with the initial base design. Then what we can do, I would like to draw your attention to the figure on the bottom. You see 3 colors. The black one, the core. Let's talk about an example of like a levee design. The part labeled as number 1 is the risk-based initial design. So you selected the risk threshold, and then based on that risk threshold, you had initial design. But then for practical purposes, you think, okay, if in the future I need to make any adjustments, let's consider practicality. Let's say it's a levee and on the left you have riverside and on the right you have land side. If I want to make any adjustment on the riverside in the future, it will be very difficult, practically speaking, to make any adjustment in the future. Now that um, I have access and I have construction crew and equipment at the site. Let's include that section two, the blue section, which we call it adaptation capacity. What does it mean? It will build the capacity for any future changes in the area. And then we start construction with the design with adaptation capacity. Then keep observing key climate variables and updating climate model simulations based on that, and also based on monitoring the structure performance, update failure probability based on new observation and updated climate model simulation. If the updated probability of failure still meet the criteria, you're good. If it's not, then what you need to evaluate the modification required and then construct or implement modification and adaptation. So with that approach, this is a simplified, a shorter version of the framework that we propose. You can basically avoid overinvestment upfront. At the same time, you are building capacity for future modification in the design. Um, Quickly, I'm showing a design example of seawall design for Los Angeles area. Here, what you can see high water, tidal high water likely for different scenarios versus high water elevation above historical mean higher than high water. So as you can see, you can have different scenarios. Just take a look at the 2100 low and 2100 high. So it depends on how much you can go above the high water compared to historical. Look at the difference. It can be basically anywhere between 1.6 to 2. Now, we want to design a seawall. The question is, how can we do that? Which one should we select? For this particular one, this is an example showing how you can incorporate that. This on the y-axis, you see tidal water level, and on the x-axis, you see lifetime of the structure. So what we did in this particular case, we went with like 2100 low, which gave us 1.6 meter above basically historical data. We selected, we considered that for our design purposes. And then what we did was we kept monitoring the structure. And that's what you see using the stars. And we kept monitoring, and as soon as we saw the deviation from most likely sea level rise scenario, we revisited the probability of failure of the structure and looked at the distribution. If the probability of failure of the structure exceeded the threshold that we have, it means that we need to start making modification in the design and in the design of the structure. In this case, seawall, it will be increasing the height of seawall. And here is the figure for failure probability, the same thing. The lower bound is when we consider stationary basically failure probability. The upper bound is non-stationary. Basically, that's the worst upper bound of the scenario that we have. It depends on what we want to do. We do not suggest to go all the way with the worst case scenario from the beginning. We want to have an basically monitoring the climate projections, and that's what we basically propose with that solid black line in the middle. And as soon as we exceeded, we passed the threshold, the acceptable threshold, we start making modification. And that's where you see that green arrow showing that you need to make adaptation modification. It depends on where you are. You can see decreasing failure probability due to adaptation. And And you can see increasing failure probability due to non-station. So that was a simple example to show that we can consider future climate projection or design practice. We do not need to go with the worst case scenario in the beginning. We can adopt this observational method notion and keep monitoring the structure and climate simulation. With that, I want to wrap up my presentation with a few concluding remarks. First, on the first part that we talked about analysis, we said resilience under a changing climate poses a new class of problem. In geotechnical engineering and structural engineering, that we need to look at multi-physics, multi-scale problems. What we need to do, we need to do fundamental research to improve our understanding about stationary and non-stationary climatic trends, their impact on soil behavior, as well as loading conditions. There are historical data and trends clearly showing increased intensity or frequency of extreme events, which is consistent with uh, uh, climate modeling projections. Adaptation to climate change requires us to quantify the impact of climate change on the performance of infrastructure. We saw that in some cases, using historical data can lead to underestimation of their impact on the behavior of earthen structures. As I said, it depends on the site, it depends on the structure. It may be significant in one side, but it may not be as significant in another side. In terms of design, we need to revisit our design code with a vision toward embracing climate adaptive methods. There is a huge variability among climate models, but we can see that intensity and frequency are projected to increase in several regions. We propose a framework for linking climate extremes to exposure of infrastructure system and to adapt to climate change. We started with initial design with adaptation capacity, and we kept monitoring the infrastructure performance and climate model simulation. And based on those, we decided if we need to make any modification or adjustment in design. This methodology can work for some structures or earthen structures, but may not work for all the structures. There are some limitations, but of course, we need to still work on it. I just wanted to briefly introduce two related documents. In 2018, I'm a part of ASD committee to adaptation to a changing climate. We published a manual of practice in 2018 called Climate Resilient Infrastructure. Very interesting document, very good reference for different areas related to climate resilient infrastructure. Another document that will be published soon is we have a white paper basically to which is titled Prioritizing Action to Adopt America's Infrastructure for Climate Change. It will be published soon, and it can be a good reference for all who are interested on climate adapted infrastructure. With that, I'd like to conclude my presentation. I'll be more than happy to answer any questions if you have any.
Thank you very much, Dr. Vahedifard. Very interesting talk. So questions, you can use the chat window or unmute yourself. In the meantime, I do have a question. I have several questions, but so you consider the projected IDF curves at daily range. Now there are two related questions. One is, what about smaller scale, stop daily? Does it matter? Does changes in, for example, 2-hour rainfall, extreme rainfall matter or not, versus I don't know, a 10-hour rainfall, for the stability of the or any for the landscape? And the second one is when you consider maybe a few days of rainfall, like a maximum 7-day. I assume that's the total 7-day precipitation. Do you think the intervals between the events matter or not? You might have a 7-day event where in the first day and last day you had very heavy rainfall, that in total they resulted in a high extreme event, or you might have a few consecutive events. If you can clarify those, please. Thanks.
Uh, Great questions, Reza. For the first question, what we did basically we looked at different rainfall duration as well. So we analyzed the slope for 1 day duration, 3 day duration, 7 day duration of rain. So we looked at different duration. As you know, when we are dealing with shorter duration, we are talking about a higher intensity of rain. So the performance of the slope is different for different scenarios. Uh,
Sorry, I'm talking
we
about sub daily, less than 1 day. Is it more?
That's that's a good question. For landslides, we have historical data for each slide that it tells us, for example, what's the threshold for initiating a landslide in this particular area. For example, for Seattle area, based on the available data that we had for the slide, we noted that the minimum rainfall initiating a slide is about 24 to 36 hours. So in the simulation that we did, we just looked at daily rainfall or the minimum 24-hour rainfall. We went up to 7 days, but that's a good question. We also looked at shorter duration rainfall for another slide that we had in California. But for that area, for Seattle area, the minimum rainfall, and that's based on the data that we collected for a relatively long period of time from USGS, the minimum rainfall triggering a landslide it was about 36 hours or something like that. Uh, uh, there are a lot of empirical correlations to basically describe the threshold for that duration or intensity of rainfall, just basically based on the history of the area. But that's a good question. For the second question, in case if I understood your question correctly, you were asking if we have multiple rainfalls with gaps. uh, the soil behavior is very sensitive to initial condition. That's a great comment. Where uh, sometimes when you have even a non-extreme rainfall happening back to back, that can bring the slope to a state of failure. So it will have like incremental impact. And so you have and we did see actually we had a similar case, not for a landslide, but for a levee failure in Louisiana. We looked at that for a flood case. The flood by itself, it wasn't an extreme flood, but it was combined with another rainfall happening in like a few days before the flood. The combination of the two, and that's what we call it cascading or compound events. So they intensify each other impact. But for particularly for soil, uh, the initial condition has a very critical role. So sometimes you just need one last push to basically fail the structure. We did look at this aspect in another study area, but I didn't present it here. But that's definitely relevant.
All right. Thank you.
Mhm.
Thanks. A question from Vinay. Um, I have a question about climate resilient infrastructure. Do you feel when it comes to civil engineering design, we need to incorporate more hybrid models? For example, climate effects of soil behavior affecting foundation behavior for buildings.
Uh, I think hybrid models. I'm not sure if I fully understand what you
Vinay,
mean by hybrid.
if you want to elaborate on that, you're welcome to.
Um, yeah, so what I was just sorry, what I was just trying to ask is because I'm a master's in engineering student, structural engineering, and and from from what I know that when it comes to designing our structures, we have to understand, well, not understand, but we have to uh, interact with the geotechnical engineers to understand the how the soil behavior can affect can affect the structure. So what I'm trying to ask is, given how much you've shown through your slides the variability of, like for example, the slope stability for certain soil types. What I'm kind of trying to ask is, due to that variability, do you feel that we like for us as engineers, we have to study the how the behavior of soil can affect the behavior of another structure it's interacting with?
That's a very good question. As I said in one of the slides, I think we need to understand and study the impact on both factors controlling design, and that's supply and demand. Supply is the performance of the soil. Yes, we need to understand the performance of the soil, like shear strength of the soil under, just as an example, we see that based on historical records and based on projections, we see that we have more and more frequent drought seasons, or we see more and more extreme drought, wet season cycles. From a geotechnical perspective, what's the implication of a drought season? I can see that when I have more severe drought, there is a higher chance of desiccation cracking in soil. So there is a fundamental science piece in that. It doesn't have to do with the source or the triggering factor for climate change. But for me, I need to better understand if I have more extreme droughts, what will be the implication on soil shear strength? Then on this design part, we need to also understand the loading condition. We use hydraulic loading examples, which are like extreme precipitation or flooding. In terms of design, I think we can do that. We can incorporate those into design uh, practice. Um, there are several challenges here. The variability, the scale, those are some challenges that we deal. But I think we can tackle that, and we have to start dealing with that, because with the trends that we see, it's almost inevitable that we have to deal with these new patterns soon. So the way to do that is to go and deal with that, how we can quantify or design parameters constraining those. For example, we are adopting this more probabilistic or reliability-based design frameworks. As a relevant example is LRFD. LRFD is getting more and more attention. So we are trying to consider that uncertainty. So I think we can adopt kind of similar approach when we are dealing with climate projections to address that.
All right. Question from Omid. I think you have addressed it if you want to add anything to that. Regarding the design of the infrastructure, which one of the characteristics of precipitation, like duration or frequency, have a greater impact on the soil behavior?
It depends on the site and the application of the infrastructure, the functionality of the infrastructure. One thing that we are recently focusing on is on the impact of heat waves or drought season. In some areas, when you have fine grained soils like clay and silt, we see that it can cause significant issues in terms of soil desiccations, in terms of land subsidence. In some areas, when they're landslide prone areas, we see the effect of extreme precipitation is very significant. In areas protected by levees, changes in flooding has significant impact. Again, it varies in different areas based on the functionality of the structure, based on the location that we're talking. But all of them, they can have different impacts on the structure and also soil if we talk about it. For example, if we are designing a seawall or we are designing a levee, sea level rise has a direct implication. Flood will have direct implication. Extreme precipitation will have direct implication. For levees, a few years ago, we looked at the effect of drought on levees structure. It's not intuitive that you think, oh, drought may have impact on levee structure by itself, but we did show that it can have significant impact on levee structure itself.
And one last question from Sohail. I think knows it very well. Um, is it reasonable to consider a conservative climate model change or the worst one in terms of the impact of for risk assessment framework? Or should we consider a bunch of models and look at the band of projection, especially when we want to assess the risk for a specific structure like earthen, not for the network of assets?
Uh, in the framework that we propose, we propose to not go with worst case scenario for initial design, because worst case scenario will pose huge cost to the project. And that's something that we need to consider. There is a huge challenge in adaptive infrastructure, and it's to attract investors, to convince, even agencies or owners to invest in, adaptive infrastructure. They may say it's too much, it's too conservative. So for that reason, we suggested to not go with the worst case scenario. We said for each case, for each infrastructure, first identify the risk threshold that we can tolerate for that particular infrastructure, particular area. Based on the risk threshold, select somewhere between lower bound and upper bound, and that was the distribution that we showed in the presentation. And then go with that risk-based initial design. At the same time, we suggested, based on the type of structure, consider adaptation capacity for the areas that can be easier to make changes right now versus waiting for future to make changes in future.
Great. Thank you. Thank you very much, Dr. Vahedifard, for the excellent presentation. It was really interesting, a nice example of an interdisciplinary research work. Several, actually, a couple of examples. I hope we can have you present in the future with more of your discoveries, etc. And yeah, maybe soon as in person in London.
Thank you so much. Thanks a lot for having me. It was a pleasure talking to you all and share some of our recent findings on this area. And yes, I do hope we can meet in person in the near future. But thanks again for having me.
Great. Thank you. Have a great day. Thank you, everyone, and see you next week.
Thank you. Have a good day. Bye.